This module shows the procedures for testing the null hypothesis that two population means are equal when you have evidence that the two populations have different variances. We've talked about this situation in previous modules, and so now it's time to deal with this particular situation. And earlier we tested hypotheses about two population means based on data from two independent samples, under the assumption that the two populations had the same variance. And for that circumstance, we calculated what we call the pooled estimate of the common variance by computing a weighted average of the variances from the variance from sample 1 and the variance from sample 2. And that weighted average we called S sub p squared, or the pooled estimate of the common variance. Now, when we tested the null hypothesis that of H sub naught, that mu1 equals mu2 versus the alternative H sub 1, that those two population means are not equal, we used the test statistic shown here, t equal x1 bar minus x2 bar divided by S sub p times the square root of 1 over n1 plus 1 over n2. And you'll recall that we have in the numerator of this test statistic the difference that's of interest to us, that is the difference between the two sample means. And we have in the denominator then the standard error of that difference. Now, in this current circumstance, what are we going to do if the two population variances are not equal? Clearly, if they're not equal, you can't use a weighted average of the variance from sample 1 and the variance from sample 2 to get a common variance, because there's no common variance. Now, you may recall from the discussions we had earlier that if you have this entity called the variance of x1 bar minus x2 bar, as shown on the slide here, that variance is equal to the sum of the variances for x1 bar and the variances for x2 bar. So that variance is x1 squared, sigma 1 squared, I'm sorry, divided by n1 plus sigma 2 squared divided by n2. And here we're going to have to estimate that by s1 squared over n1 plus s2 squared over n2, because we can't pool these two variances to get a common estimate. Now, this changes the situation somewhat, and so we have to figure out how to deal with this changed situation. And it's not surprising that we would want to test the null hypothesis that the two population means mu1 and mu2 are equal with a test statistic that looks like the one shown here, that is with x1 bar minus x2 bar divided by the standard error of that difference, or basically the square root of s1 squared over n1 plus s2 squared over n2. The question is, where do we look up the number in a table for this situation? Well, there are, in different textbooks, two different ways for handling this situation, because we need to make an adjustment. In some texts, the adjustment is made by calculating a slightly different test statistic. In others, the adjustment is made by calculating different degrees of freedom than the one you would get by simply adding up the degrees of freedom for sample 1 plus the degrees of freedom for sample 2. Now, the strategy I will show you is the latter. I will show you how to do this and how to make this adjustment by calculating an estimated degrees of freedom. The only reason to go through this is to get a better approximation for the t distribution to use to compare this t statistic result against. So we're going to calculate the test statistic shown here, but we also have to come up with a different degrees of freedom. And that's a little bit of a cumbersome entity. And in fact, as you see here on this slide, it is a very cumbersome looking entity. This estimated degrees of freedom that we're going to use, we have to calculate, and we calculate it by this somewhat complex formula here. That is, this estimated degrees of freedom, F is equal to S1 squared over N1 plus S2 squared over N2, that whole thing squared, divided by S1 squared over N1 by itself squared, plus S2 squared over N2 itself squared. And each of those are separately divided by, the first one is divided by N1 plus 1, the second one divided by N2 plus 1, as shown. Do that calculation and you subtract minus 2. Now that really is a cumbersome looking formula, and it is actually a little bit aggravating to have to calculate. But it does give you a good approximation for this test statistic. Now, in order to show you that, we'll work through an example here. And This example says that we have a random sample of 5 persons from a male population and 10 persons from a female population. And what was being measured in these samples was histidine levels. And we're going to assume that these measurements were approximately normally distributed. And then we have the data that's shown in the table there. For males, the mean histidine level was 300.8, and for females it was 153.2. Now those are fairly far apart in terms of differences in their mean values, but also notice that the variances are, number 1, look quite large, on number 2, look strikingly different. So first one is S1, the S squared for males is 15,291.7, and for females is 2,484.62. So one of them is almost 6 times or more than the other one. And just to remind you that we could subject that null hypothesis that those 2 population variances are equal to a test, and if we did that test, we would reject the null hypothesis. So here we're going to focus on the test of the null hypothesis that the two populations have the same mean. So we go through our 7 steps. The first step is to write out the null hypothesis and the alternative hypothesis. The null hypothesis here is that the mean for males is equal to the mean for females. The population means those are. And versus the alternative that they're not equal. The assumptions that we're going to work with are that these 2 samples are independent, and that's an essential assumption. And the other one is that they're approximately normally distributed. Then we're going to use our old friend alpha equal to 0.05, and we're going to use the test statistic that I just showed you in an earlier slide, as is repeated here. But we're going to reject the null hypothesis if the value we calculate for t is not between t plus or minus t sub 0.975 with f degrees of freedom, where we have to do this cumbersome calculation. Now, if you plug all the numbers into the formula and finish the calculations there, you'll see that f is equal to 6.99 minus 2. So that's 4.99, so we'd use f equal to 5. And then if you look in the tables for t sub 0.975 with 5 degrees of freedom, you see that it's 2.57058. So then defines the critical region for us. So now we have to calculate our test statistic. And to do that, we plug in the numbers into the formula, and we get those that are shown here, that t is equal to 300.8 minus 153.2 divided by the square root of 15,291.7 divided by 5. What's going on? Oh, okay, let me back up because I hit the wrong button. So let me start over on this slide. Start over on 10. I thought I did something to the computer. Okay, ready? So to finish these calculations, we have to calculate the test statistic itself, as shown here. T is equal to 300.8 minus 153.2. Those are the 2 sample means, the mean for males minus the mean for females. We divide those by the square root of S1 squared over N1 plus the square root of S2 squared over N2, and that's the 15,291.7 divided by 5 plus 2,486.6 divided by 10. Do all that calculation and we end up with a value that's 2.57. So this raises an interesting issue, because this value we've calculated for t is very close to the cut point. And if you didn't round it off to two decimals, you might find that it was on one side or the other. So the best way to describe this is to simply say that the p is approximately 0.05. And again, what we've done with this example is we've tested the null hypothesis that 2 population means are equal, and we've done so with evidence that the 2 variances for those 2 populations are not equal, so we had to make this adjustment. And this is just another example of making a minor adjustment to a tool to fit the circumstances at hand. Now we can also calculate confidence intervals for this situation, and just for a little diversity here, I've walk through the calculations on this slide for a 99% confidence interval, that is with alpha equal to 0.01. So we have the formula for the confidence interval as shown here. That shouldn't surprise you. It looks just like you would expect it to look, I would think. You've got the two population means, and you might, in general, that why we use the notation mu1 minus mu2. In this particular case, it would be mu m minus mu f if you wish to do that. But I'll use this notation for this slide. So we've got in the middle of this equation mu1 minus mu2. In the middle of the interval, we have x1 bar minus x2 bar, and we have the information shown below the formula for the confidence interval are the numbers we need to plug into this overall picture. Notice that we've already calculated the degrees of freedom as 5, but here we're going to use a 99% confidence interval, so we need, in order to mark off the middle 99%, we have to go up to 0.005, or we can look in the t-tables for t sub 0.995 with 5 degrees of freedom, and that's 4.0321. So plugging all of that information into the equation and finishing the calculations, we end up with a confidence interval that goes from minus 84.27 to a plus 379.47. Notice this is a very long confidence interval. And notice also that, or perhaps not notice is not the right expression, we can test the null hypothesis about the difference between these two means by looking at this confidence interval. And in this particular case, we would be testing that null hypothesis at the alpha level of alpha equal to 0.01. Not at our standard one that we've used most of the time, which is 0.05. But if you wanted to test the null hypothesis that the two population means were equal, and you wish to do it with alpha equal to 0.01, you can do it simply by looking at this confidence interval, and you see that 0 is included in the confidence interval. The confidence interval goes from fairly far on the left side, on the negative side, to way far on the positive side, so it does include 0, so you would have to accept the null hypothesis that these two means were equal. Now we work through some other examples. This is an article on the association between state housing policy and lead poisoning in children. We have extracted from that article a table as shown here, and I've highlighted with the green box the issue that I really want to focus on, which is the arithmetic mean blood lead level in milligrams per deciliter. I noticed that for Providence, where there are 136 census tracts, and for Worcester there are 153 census tracts. So notice here that the unit of measurement is a census tract and not a particular not a person, so these are based on aggregate levels. But there's a 6.7 is the mean for Providence, and it says that 2.06 is the standard deviation, and we have for the other county 5.4 with a standard deviation of 1.01. Now we could I've just repeated this information in the table on this slide, and there are 3 things that I would like for you to work through and just to do on your own. I won't walk through them with you. The first is to test the null hypothesis that sigma 1 squared is equal to 6. You have the standard deviation as 2.06. The square of that standard deviation is s squared, which would be 4 something. So you would be testing whether you would be examining the null hypothesis that the true value of the population mean was 6. Your estimate is 4 something, so the fundamental question is 4 so far away from 6 for you to be able to reject the null hypothesis that 6 is the truth? The next thing I'd like you to do is to test the null hypothesis that these two population variances are equal. After you do that, then use the appropriate test for testing the null hypothesis that the two population means are equal.